And so one day I decided to try and set myself a little challenge. Can I make a container? I feel like I know a lot about containers, or at least know a lot about how to make them, but can I do it just using shell commands? Can I make something that looks plausibly like a container just using some shell commands? And after a few days, I concluded that yes, I can. Your definition of decent and my definition of decent might differ, but I think it's kind of decent. It's not perfect. There's some messy corners. There's some steps you have to do manually still. And there are one or two things you simply can't do. So I don't do them. For instance, I have no setcomp system call filtering because there is no shell command to set that up. But it is just standard shell commands that you'll find on any Linux distribution, and it gives a reasonable approximation of what kind of isolation you would have in, say, a Docker container. The shell commands I'm going to use, aside from the standard commands that you'd know about every day, some less common commands that I want to use, Unshare, the mount command, and the pivot root command. All those commands are built on top of system calls that have exactly the same name. Basically, they tend to be sort of pretty thin wrappers on top of the actual system calls. And I'm going to use Busybox, because Busybox is great. It gives me one binary that does a few hundred different things, gives me, I don't have to put a few hundred different shell commands into my container. I just put Busybox in there and I've got something that's usable. Okay, Busybox implements the core functionality of about 400 different shell commands, but it does it using just one statically linked binary. And so I don't have to copy in 400 binaries and shared libraries into my container to set things up. I can just do it really in a couple of steps. It is all shell commands, but of course I'm not going to type all the shell commands. I've put them into scripts. And what I'm going to do is just talk us through the scripts. And so I've got three principal scripts. One is a script that creates the file system that my container is going to use, because a container needs to have a file system. And so I need to build that file system. The next script launches the container. It does a number of things to get the container ready to go, and then it launches it. And then there's one more script, and this script is automatically executed once the container has been launched. And it does some steps that need to be done inside the container after it's been launched. So the various pieces. Our container needs a file system, and a root file system, so-called. And of course, each container should have its own private file system, so that when one container changes files, of course, that doesn't affect other containers. Each container is going to have some files that are unique to that container, but there's a lot of files that are the same in every container. For instance, every container is going to have a bin directory with some binaries in it, and they're the same binaries. So there's a lot of duplication in terms of file system content across the containers. Now, if the way we did things was each container gets a separate copy of all of the files, that would be a bit of a problem for a couple of reasons. One is a lot of wasted space, because a lot of containers that mostly have the same file system content. So we've just chewed up disk space for no reason, and chewed up memory as well. The other thing is that when we launch the container, because the container needs to be launched with a file system image, we need to copy all of those files. That takes some time. That would make our container start up a little bit slower. The solution to these problems is to use what's called a union mount. Now, a union mount is really just a technique for combining the contents of several different directories, stacking them up in a way, and providing a merged view of that stack of directories. And the idea is that you have, in the lower part of the layers, one or more read-only directories. And then on the top layer, you have a read-write layer, a read-write directory that is the differences between the contents of the lower layers. And it's that read-write upper layer in each container that is going to contain the stuff that is unique for each container. But the lower layers are going to be actually the same files, same directories across all containers. The idea then is, lower layers or lower layer is content common to all the containers. Upper layer is the stuff that is private to individual containers. There's a few different ways of doing this. The modern way of doing this, this is used by Docker and Podman and a few other tools, is to use a union mount file system called OverlayFS. There are other ways. There's a few other techniques I've just listed there at the bottom of the slides, including some predecessors of OverlayFS, UnionFS and AUFS. The idea with OverlayFS is you mount an overlay, you create an OverlayFS mount by specifying what directories are going to be part of the mount. And so here I've got a mount command where I'm saying it's an overlay mount, and then I specify elsewhere in the mount command what are my layers. And here I've said my lower layers, and this is a list of directories. Now in this particular case, I've specified 2 directories separated by colons, okay, lower 1 and lower 2. And then elsewhere, I specify what directory is going to be the upper layer. And then there's one more thing that I need to do as part of that mount, is to create what's called, or to also specify a directory that's going to be used as a working directory. Now this directory is used behind the scenes by OverlayFS for doing sort of temporary setup for files. Sometimes there are certain actions that need to be done, and then once they've been done, the resulting file needs to be moved into the upper layer. But before the action is complete, that file shouldn't be visible in the upper layer. And I give an example, for instance, here, suppose you do an echo command and you say, I want to add some content at the end of a file that's in a lower layer. Now, ultimately, what you end up with in the upper layer is a complete file with that additional content. But until that complete file has been built, you don't want the partially copied file to be visible because it's not yet completed. And this is done in the working directory. The work directory needs to be on the same file system as the upper directory, because what's going to happen is when the work is finished, when the setup work is finished, what happens is the file gets moved from the work directory into the upper directory just using rename, and rename is atomic. Okay, so if I do a mount command like that, the arrangement I'm ending up with is like this. I've got a series of stacked directories, and they're stacked up like this. Lower 2, lower 1. Notice the order there corresponding in the command. The first named lower directory is the one that's at the top of the lower layers, and so on. And then above that, the upper layer. And what I also specified as part of my mount was the location where the mount is, the merged view of all of these directories. And so what I'm going to be able to see in that merged view is the combination of everything that's visible from the lower layers. Now, of course, you could have, in the different lower layers, files that have the same name in the same place. In that case, the file you actually see in the merged view is the one that is in the uppermost layer. So you can see here I've got a file called all that is visible in all of those lower layers, or it's part of all of those lower layers. The one that's visible in the merged view is the topmost one, the one from the upper directory. Here I've got a file that is present in 2 different path names in the 2 different lower layers. The one that's visible at the top is the one in the uppermost layer. You can also have the concept where you have a file from a lower layer that has been deleted. And of course, therefore, it shouldn't be visible in an upper layer. And the way this is done is by creating what's called a whiteout, and that's just my way of representing a whiteout. A whiteout is a special entry in the file system that is basically saying, hide the thing that is below. And so you can remove files or make them become invisible from the lower layers using a whiteout, or that's what the file system is doing for you. Okay, so what I'm going to do for my container is have an overlay file system where I have a single lower layer, which is the contents of the files that are common to all of my containers. It's going to have my bin directory and things like that, for example. And then my upper layer is the differences, the stuff that is unique to this container. I've got my script that builds that lower layer. And I give one argument, just the directory where that lower layer, or the path name where the directory containing that lower layer should be constructed. What I do is, in the script, make that directory, step into that directory, and then I create the kinds of directories you'd expect to see in a root file system. Bin, dev, etc., and so on. Then I step into the bin directory and copy in Busybox. Okay, the which command, if you're not familiar with it, just tells you what's the path name where a certain command is located. So I'm just using command substitution there to get the path name of the Busybox binary. And I copy it into my bin directory. And then Busybox has this really cool feature where it emulates the functionality of about 400 different shell commands, and the way that it does that is there are links to the binary with 400 different names. A link called ls, meaning Busybox should list files. A link called rm, meaning that Busybox should remove files. And of course, one of the things I need to do is construct the links. Well, Busybox does that for you. You can say Busybox, you need to give a full path name, -- install dot, and it makes the links. And after I've done that, I've got about 400 links to the Busybox binary in that bin directory. Okay, so that's my file, or the start of my file system at least. Now, in our container, we need to be doing various kinds of isolation. The whole idea of a container is to provide an illusion that there is no outside world. There's a bunch of processes inside the container. They seem to be in a world of their own. There is no outside world. And how do we provide that illusion? And namespaces are a key part of that illusion. What we want to have for a container, each container should have its own set of mounted file systems, have its own host name, have its own network infrastructure, a private set of PIDs for that container. And one of the reasons we want to be able to have that is we want in each container to have a PID1, an init process. Init is a rather special process on classical Unix systems, and it's special in containers as well. One of the things that init does, for example, is when a process becomes orphaned because its parent terminated, the orphaned child process gets reparented to the init process. And of course, we want that to also work inside the container, so that if a process inside the container becomes orphaned, it gets reparented not to the init process on the outside system, but rather to the init process inside the container. We also want in our container the concept of superuser, a privileged processes that can do superusery things inside the container, but are not privileged outside the container. And again, namespaces allow this possibility. So the general idea of a namespace is to isolate some kind of resource and make it seem like there is a private copy of that resource for a certain group of processes. We've got a number of different types of namespace. I'm not going to talk about all of them, but here's a few examples. PID namespaces. These make the set of PIDs private to to that group of processes. And in particular, as I've mentioned already, this means that we can have a PID1 in our container. We've got mount namespaces. What mount namespace is doing is isolating the set of mounts. This means that different groups of processes can see different sets of mounts and therefore different single directory hierarchies, different sets of mounted file systems. UTS namespaces are the simplest one. All they're doing is isolating a couple of system identifiers, notably the host name. And this means each one of our containers can have a different host name. The container can broadcast that host name on DHCP, so it gets assigned an IP address. And we've got network namespaces, which of course are also rather important because it means each container can have its own pieces of network infrastructure, its own virtual networking device with an IP address, its own set of socket port numbers, its own routing table rules, its own firewall rules, and so on. And the idea of course, is let's make our containers useful in a networking sense. For our container, we're going to create one namespace of each one of the types. I've talked about 4 namespace types there. There are 8 types of namespace altogether, but I'm not going to talk about all the others. So then the question is, how do we do superuser inside a container? And that concept is supported by another type of namespace called a user namespace. And what user namespaces are doing is isolating the user ID and the group ID number space. What this means is that you can have a process that in the outside world has an unprivileged user ID, maybe user ID 1000. But inside the container, it has a different user ID. And in particular, the interesting case here is a process that inside the container has UID 0. It has superuser powers inside the container. Now, the other piece that goes along with user namespaces here is capabilities. Capabilities are the modern way of implementing privilege on Linux systems. The idea of capabilities is let's break the power of superuser into smaller pieces. There are currently 41 of those smaller pieces. And what we think of as being classical superuser nowadays is really conceptually just a process that has all 41 of those capabilities. And processes that have UID 0 normally have all 41 of those capabilities. So we're going to create a new user namespace for our container. One of the things that happens when a new user namespace is created, the kernel magically says the first process that's created inside that user namespace, you shall have all capabilities. It's just a thing that the kernel does. And so as a consequence of simply creating a user namespace with a process inside it, that process has all 41 capabilities, which is great. It's a super user process. We wanted one of those. The way we create a namespace at the shell level is a command called Unshare. It's a funny name, but there's a funny history behind it. And it's built on top of the Unshare system call. And so we can do something like this, for example. Here I'm saying unshare --user, create a user namespace, --PID, create a PID namespace as well, --fork, create a child process. Okay, because I want a child process that I'm going to use to execute a command. And then the rest of the line is the command that's going to be executed by that child process. And I've said, my command is a shell. And it has some options. -C says, execute the command that is in the argument, in the quoted argument there. And I say, echo my PID is $, okay, the PID of the shell. And when I do that, magically, that shell has PID 1 because it was the first process in that new PID namespace. Okay, now another part of the isolation that we want to do inside a container is Cgroups. We want to limit the resources that the processes in the container can use. We want to do that because, first of all, we want to prevent our container from overwhelming the rest of the system by trying to consume too much resource. Create too many processes, or use too much memory, or burn up too much CPU time. So that's one side of the guarantee we want, but there's also the mirror side of the guarantee, which is we want to make sure the other containers don't overwhelm the system so we can actually get something. Two sides of the same coin. But we also want to do things like limiting access to devices. Inside a container, we don't generally want the process to be able to access random devices on the system. There are some good security reasons for that. Some devices can be used for some kinds of privilege escalations, so we actually want to only allow a very limited set of devices to be visible inside a container. We do this using Cgroups. We can also use the Cgroups to measure the resources that are being consumed by the container. How much CPU time is being used, how much memory is the container using, and so on. And the way this is being done is with this Linux feature called Cgroups, control groups. The important point about Cgroups is they are allowing us to do resource limitation and resource management per group of processes. We can set a limit that applies to a group of processes. Maybe one process uses a lot of the resource and the other process uses a little, but the point is whatever we allocate is shared across the group. There were older mechanisms, they still exist, for doing resource limitation on Unix systems, the ulimit command, but the thing about the ulimit command, it is just a per process limit. The limit's not shared across groups of processes. The way that Cgroups work, the interface for controlling Cgroups, it's a file system. And in order to make a Cgroup, what we do is on that file system, it's so-called Cgroup2 file system mounted at this location here. To make a Cgroup, all we do is make a directory in that file system. And that is synonymous with the act of creating a Cgroup. And Cgroups have a hierarchical arrangement. And when you set limits in Cgroups, the limits apply to the lower parts of the hierarchy. And of course, the way we're going to construct our hierarchy is by having a hierarchy of directories. The directory hierarchy is synonymous with the Cgroup hierarchy. Okay. Now, we want to look at the commands now to actually launch our container. So I've got another script here. It takes a few arguments. One of them is the directory that contains the lower level of our file system. That's the directory that my first script created. Another argument is the location where the overlay file system is going to be mounted, my merged directory. And a couple of other possible options here, a path name that my container is going to use for its Cgroup, and also the host name that my container should set up in its UTS namespace. And I'm going to skip over some details and just say those various pieces there, my script just sticks them into some suitably named variables. Okay, lower, overlay dir, Cgroup, host. Just assume that was done. I'm not going to show you that. That's mechanical. Okay. So, having got those variables, what am I doing? Well, I'm making some directories. In my overlay dir, I'm making an upper directory. That's going to be my read-write upper layer in my overlay file system mount. The work directory that is needed for OverlayFS. The mount point. Create the mount point where the OverlayFS is going to be mounted. Then I do the mount. Sudo mount -t overlay. There's my lower directory. There's my upper directory. Here's my work directory. And then source of the mount is any string. I've just written overlay there. But then here's the mount point. And then my script steps into that directory. Okay. just by way of demonstration, I then create, my script then creates a little file with a bit of information about the startup of the script, just puts date in there, PID and one or two other things, and then that file will actually be created in the upper directory of that overlay mount setup. Now, if I specified a Cgroup when I launched my script, then this variable here will be set, and so what I'm going to do is create a Cgroup that is going to be used by this by this container. So my Cgroup path is sysfs Cgroup, that's the standard mount point for the Cgroup file system, and then whatever path, whatever name I gave as an argument to my script. I make that directory, sudo make -p, and then I say here, do a shell command where I say echo the PID of this shell script into a file called cgroup.paths cgroup.procs in that Cgroup. What that is doing, this is the way that you put a process into a Cgroup. You write its PID to that file. And so now this shell script, it's a member of that Cgroup. The shell that is running the script is a member of that Cgroup. There's a bit more. Okay, still here with Cgroups. One more thing, I do what's called delegation for the Cgroup. The files in the Cgroup file system are all owned by Superuser. So the default situation is, in order to do things with those files, you need to have a root shell. But I want to run a container for an unprivileged user. So what I'm going to do is take my sub-hierarchy there, the Cgroup that I'm creating, change its ownership to be the unprivileged user. And as well, I need to change the ownership of a certain set of files inside that directory. There's a file here, syskernel cgroup delegate, and it tells me which of those files also need to have their ownership changed. Because not all the files need to be changed, and certain files, their ownership should not be changed. But there's a certain set of files whose ownership must be changed, and as well, the ownership of the directory must be changed. So what I'm doing here is saying sudo sh-c, here's my shell command where I say step into that Cgroup and then work out which files need to be delegated. What I do is I list the contents of this file to see which files are actually present in the directory. Some of them won't be, they'll generate errors, but I'm going to throw the errors away. But the result of the ls is I'm going to have a list of files that actually exist in the directory, and then I say that's my list of files, and then I say chown to my user ID, my group ID, the unprivileged user and group, and on dot, the Cgroup directory, and that set of files that I've discovered inside the directory whose ownership needs to be changed. Okay. Now, the next step in my shell script, I use exec. Now, I don't know if you're familiar with the shell command exec. What exec says is replace this shell with a different program. It's the same process. It was running a shell, but now the shell is saying, I don't need to be here anymore. Replace me with another program. And the program I'm replacing the shell with is another program called env. Now, env is a program that does things with environment variables. And what I'm doing here is saying env-i, initialize some environment variables. I'm going to initialize the environment variable home to be /root, my home directory, for my superuser shell that I'm going to have inside the container, and initialize path with some suitable list of path names. Set host name to whatever was supplied to the script. And then one more environment variable that I'm going to set up here is called env. I'll delay explaining that just for a moment. All I'll just say is that I'm setting up that environment variable to point to another script. I'll show you that script in a moment. Okay, and then, having done its work, env then itself does an exec operation to replace itself with another program. The program I'm replacing it with is Unshare. And what I'm saying with Unshare here is create a new user namespace with the so-called, in fact, I'll just jump forward a slide or two here, create a new user namespace, and then with the root mappings. Root mappings means my credentials in the outside world are going to be mapped to 0 in the inside world. So in the outside world, I might have had user ID 1000, but in the inside world, I want UID 0. I want superuser powers. Same thing for the group ID. The group ID also gets mapped to 0. So we end up with a process that has UID 0, GID 0 inside the namespace. And then as well, I'm saying create a PID namespace, create a child process, because that's going to be the process inside my container. And then I create the other kinds of namespaces as well. A mount namespace, a network namespace, an IPC namespace, a UTS namespace, and a Cgroup namespace. I haven't talked about all of those, but that doesn't matter. And then Unshare is going to launch a command in that child process. What command am I going to launch? I'm going to launch Busybox. Okay? And when you launch Busybox, you can say, what do you want it to be? And I'm saying, I want my Busybox to behave like a shell. Okay? And this is going to be my very first process inside the container. It's a shell, it has superuser powers, and it has PID 1. Okay. Now, I could have just written, instead of Busybox.sh there, I could have written just bash, but I wanted to use Busybox.sh because I want the initial shell to be the same kind of shell that is already available in the bin file system inside my container. Okay, otherwise I'd have a more powerful shell as the root shell, which would just, it's not wrong, it's just a little bit confusing. Okay. Ooh, hurry up. Okay, so after all of that, there's still some more initialization steps that I need to do. I'm going to do those in another script, this one consh post setup. And I automate the execution of that script. Remember that env environment variable that I set earlier on? That is a special variable that is understood by shells. When a shell is launched, it says if the env environment variable is initialized, I'm going to execute the commands that are inside it. And so I'm automating the creation of the script. I don't even need to do it manually. My Busybox shell is going to do this as it starts up. And the very first thing I do in that next script is unset env, because I don't want, when I launch another shell inside the container, I don't want it to execute that env script. That would be a mess. Okay. Now, my container inherited some mounts from the initial mount namespace. I don't want those mounts. All I really want to do is have mounted is my container root file system. And so I need to swap the current root file system with my overlay file system and make that the root file system. And there's a special command to do this called pivot root. You say pivot root and you say, this is the directory I want to be the new root directory, and I want you to move the old root directory, the old root mount, to this location instead. Eventually, I'm going to unmount that old root file system because we don't need it. In a picture, this is what pivot root is doing. We've got a real root directory. We've got some location underneath, which is where I'm going to mount my new root file system. And what's happening is all that pivot root is doing is shuffling the mounts around. It's arranging things so that this new root is now the root mount, and the slash mount here got mounted down here, so now it's sitting underneath the new root mount. That's all it's doing, just shuffling mounts around. There's a lot of rules about using pivot root. I don't want to try and explain them all. You can read the manual page, but there's a few rules like the new root and put old must not be on the same mount as the current root, and when you look at that picture, of course, well, you can work out why we'd end up with something quite circular. What else should I say? New root must be the path name of an existing mount. And the reason is all that pivot root is doing is rearranging mounts. Now, if our new root mount is not a mount, that's easy to fix. All we do is make a bind mount where we mount the same directory on top of itself, and then it looks like a mount point, and pivot root can shuffle it around. And that's what I will be doing. There's also another detail that I'm not going to try and explain, which is I need to turn off what is called mount propagation in the new mount namespace for the various mounts. And the reason is mount propagation is a mechanism that the kernel uses to automatically copy mounts from one mount namespace to another. And this happens by default, but I don't want that to happen, because if I did that and the new mounts I'm going to create got propagated to the main mount namespace, that would be a mess for everyone else. So I'm going to disable mount propagation. So to disable mount propagation, I say mount -- make r private. Private is the opposite of shared. Shared is the thing that propagates. Private says don't do propagation. Make my new root mount a mount. Make my directory merged a mount by saying mount -- bind merged on top of merged. All that did was create a mount point at that directory. And it's still the same contents that are visible there. It's just a way of making a mount at that location. Make old root fs. That's wrong. The old root is going to end up, the old root mount. And then do the pivot, where I say make merge the new root and move the old root to merged old root fs. Then, simple stuff here. I want some other nice stuff in terms of mounts in my container. Mount a proc file system, mount a sysfs file system, mount a Cgroup file system, mount an MQ file system for my POSIX message queues. That's all simple stuff. And then I want some devices. This is the standard sort of set of devices you'd find inside a container: full device, null device, random, TTY, urandom 0. When I first learned how to do this, I was kind of surprised that it works, but it does. I say, in the dev directory, make a file with that name, and then mount -- bind from the old root file system in the dev directory, bind mount that device to /dev in my new root mount. And this just works. I was surprised that it just works, but it does. And this gives me those devices. And then I don't need the old root mount anymore, so I do an unmount of that old root mount. That throws away all the old root mount and all the submounts underneath it. And then I can remove that directory. Then I set my host name from the environment variable that got set up earlier on. And that's it. Oh, what time was I supposed to finish? Was it about 10 o'clock, I suppose, was it? No, sorry, 11 o'clock. Maybe the second half is just going to be demonstrating how this all works in practice. Okay, and we'll see how things look. But maybe there's some questions first before we... Yes, please, down the back. Ignat, I recognize you.
I'm going to...
I think you're good. It's just...
Hello?
Yeah.
So it's recording. Like, in your presetup script, you're first creating the merged view using OverlayFS and then creating the container.
Yeah.
And for that, you need superuser privileges in the host file system. Do you think it's possible to arrange it in a way that you can do it from an unprivileged user? For example, if you create a user namespace first and then create OverlayFS inside the namespace, so perhaps you can do everything without having superuser privileges.
But hang on, I'm a little puzzled there. You say I needed superuser privilege, but when I created that lower directory, I didn't use any superuser powers.
No, I mean when you did the mount OverlayFS.
Yeah, and that mount was being done. Yes, okay. I think it is not possible to do that step from within the container. I'm moderately sure of that. I want to double check, but I think it's not possible.
Because I never researched how that works
Yeah.
inside, but like there is a project called rootless containers, and I just recently, yesterday, Docker has like you can switch a runtime to a rootless runtime where you can run Docker as an unprivileged user. So they might be doing some tricks like with unprivileged user namespaces there.
I'm not sure what they're doing there. I'm sorry.
Thank you.
I think not, because the point is that inside a user namespace and a new mount namespace, there's only certain kinds of mounts that you're allowed to create. For instance, you can't mount block file systems from a non-initial user namespace. And I think the same is true for OverlayFS as well.
Okay. I mean, I'll research that myself as well.
Okay. Other questions, perhaps? Okay. Maybe this better be the last question, I guess.
You just briefly mentioned that the seccomp will not work inside of this, but
it's not that it will not work.
Okay.
It's rather there is no shell command that I can use to set up seccomp filtering.
Oh, so that was the entire reason. It
Yeah,
doesn't have a shell. Okay. Yep.
You give me a standard shell command and I'll use it, but there isn't one. LD preload. Well, Ignat is the person to talk to about that. Yes, I know. I looked at your talk just last night, actually. Yeah, you can pull some tricks with LD preload, but those tricks are not bulletproof, and it's not a complete solution either. Okay. See you, if you want, in whenever the next session starts. Is it 20 minutes? What? 40 minutes. 40 minutes from now? You still have 20 minutes. I still have 20 minutes? What? Oh, here I was thinking I was supposed to be finished by now. Wow. Okay. Oh. Thanks for that. Then I'll keep going. Let's launch our container. I'm going to do these steps. Let's do a live demo. Live demos are the best because they can go wrong. Some people have already heard the joke, but many years ago a training colleague said to me, never precede any live demonstration with a statement more predictive than, watch this. Okay. All of the scripts, by the way, that I've shown you, they're all on my website. You can download the tarball in the location that's at the end of the slides. Okay, so my scripts. What I'm going to first of all do is make a directory. Let's call it demo. And this is where I'm going to make my container file system. So I'll step into that directory. And I'll make the font size. Is that font size still okay down the back? Yep, thank you. And then I'm going to use my script that creates the lower level layer of the file system. And I'm going to make that lower layer in a directory called lower. Okay, it's done its thing. If I look inside that directory lower, I've got a bunch of subdirectories, reasonable sorts of things you'd expect to see in a root file system. And then I'm going to run my next script. Whoops, wrong. My next script, it takes as arguments the name of a Cgroup. Let's call this CGR1. And I should have said, by the way, I am doing all of this. Here's just to show you these two shells. It is I'm doing this as an unprivileged user. And one other thing I want to show you over here. This is the host name on my outer system. Okay, and in my container I want a different host name. let's say VN, and then my lower directory, which is just called lower, and then the place where I want the rest of the pieces to be created for the overlay mount, which is just the current directory. And when I do that, I'm going to be asked for my password. Okay, that is now my root shell inside the container. And if I say echo $, 1, if I say show me my IDs, 0, okay, UID 0, GID 0. If I say what are my capable, no, let's try something else. Let's try this. The processes that are in the container. Well, there's the shell and there's the PS. That's it. If I said, let's say PS, PSA, list all the processes. There are just 2. Okay. Then what else should we see? In the outside world, in the PID namespace in the outside world, this process, this Busybox shell, has a different PID. If I say PID of Busybox, I hope I've only got one of them running. Oh yes, good. It's got a different PID. This process in a lower level PID namespace in the container has 2 different PIDs, a PID in its PID namespace, but also a PID in the upper level PID namespace. You can actually see this in the proc file system. I can say grep for a field called nstgid in the file proc/113198/status. This shows at this PID namespace level what are the various PIDs of that process, and 2 different PIDs. Now, as well, if I look at that file using less, remember over here, the process has UID 0, GID 0, but if I look from the outside world at the UIDs and the GIDs of that process, in the outside world, it has UID, GID 0, 1000 I should say. Okay, in the outside world, this process is not privileged, but it is privileged in the inside world. Okay, and of course, one of the things I did over here was, the script set a host name. There I'm seeing the host name BN. Over here, in the initial UTS namespace, I'm still seeing the host name Wanaka. If over here, I now change the host name, Langvid, and then just verify that change was made. Okay, now a different host name there. And over here, the host name is still Wanaka. Okay. Now, any other demonstrations I should do? No, I think I've done that. Let's move on. So, these are the steps where I launched my container, just on the slides. Everything's on the slides. So then the question is, what about the namespaces inside my container? Well, we saw that my shell has PID 1. That's because of the new PID namespace. We saw that outside, the process has a different PID. And the point here is that PID namespaces exist in a hierarchy. Each PID namespace has a parent PID namespace, which has a parent, and so on, all the way back to the very first PID namespace on the system, which doesn't have a parent. And a process that's in a lower layer PID namespace has a PID in that namespace, but also in the first ancestor, and then the next ancestor, and then the next ancestor. Probably the PID is different in every namespace, but the point is it has a PID in each namespace. And we've also then got the idea that the container, of course, has a file system. And so what I should really do is a live demo there. Again, my PID of my Busybox process, that number just here, let's from the outside world do a find mnt dash o source target, that'll target, and then I think it's dash T, I think it is. That was what was on the slide, wasn't it? No, dash N 113198. Show me the mounts that process sees in its mount namespace. And I see a very small set of mounts, really, compared to what you would normally see on your wider Linux system, where you probably see a boatload of mounts. Okay, there is the root mount, there's a proc mount, a sys mount, an MQ file system, some dev mounts. Those were my various devices that got bind mounted, and that's it. Okay. I've already showed you the credentials of the shell from inside and outside. How did that happen? Why is it that this process here looks like it has UID 0, but over in the outside world looks like it has UID 1000? It's because along the way, I used an option with Unshare saying map root user. What map root user did was create what's called a UID map for the user namespace. And the UID map says, what do IDs in the outside world map to in the inside world? And if I look at the UID map for that process, if I say cat/proc/UID map, there's the mapping. It's saying inside the namespace 0 maps to 1000 in the outside world, and the length of the mapping is 1. So only a single UID is being mapped. You can have mappings that are ranges of IDs by having a number that's bigger than 1 there at the end. I've got a similar GID map. Looks exactly the same. Mapping 0 to 1000 in the outside world. Okay. I've already shown you the hostname stuff. I've got 5 minutes. Let's keep going. The question is, how do I get to be superuser inside the container? And how does being superuser work, even as a concept inside the container? And the point here is it's all about namespaces and the relationship between user namespaces and non-user namespaces. Every non-user namespace is owned by some particular user namespace. And when I say a non-user namespace, a mount namespace, a UTS namespace, and so on, every one of those non-user namespaces is owned by some particular user namespace. And being superuser means you have superuser powers over the resources that are governed by the non-user namespaces that are owned by your user namespace. Now, what happened was that in my container, I think I've got a picture coming up. I should say, we can see that my shell has all capabilities, because what I can do from the outside world is look in the proc PID status file, and down below there's some lines here that tell me about the capabilities that this process has, and the numbers you're seeing there, those are hexadecimal bit masks representing the capabilities, and there are 41 bits that are on there representing all 41 capabilities that this shell has. The kernel just magically did that. It said, you are the first process in a new user namespace, and you shall have all capabilities. But those capabilities can only be exercised in the user namespace. Okay. And there's the picture I wanted. Here's the setup we've ended up with. Here's our container, like this. It's got a user namespace, and there's a number of other namespaces, a mount namespace, a time namespace, UTS namespace, and so on, that are all owned by that user namespace. And our init process is a member of all of those namespaces. I haven't shown all the namespaces because I don't have enough space on the slide, but that's the arrangement that we have. And just wondering if I've got another, I need to check if I have another picture that might be useful. Not in the slide deck, okay. The point here is that, suppose this process tries to, let's say, change the host name. What the kernel says is host names are governed by UTS namespaces. And then the kernel says, well, which UTS namespace is this process a member of? And the answer is this UTS namespace here. And then the kernel says, well, which user namespace owns that UTS namespace? And the answer is this user namespace. And then the kernel says, well, what capabilities does this process have in that user namespace? And it needs to have a certain capability called capsysadmin. But the point is, the process, this notation here is the notation that says the process has all capabilities, and it is a member of the user namespace. Therefore, it's allowed to do that thing. But for instance, if there was some way that this process could see the initial UTS namespace, even if it could somehow see that namespace, it wouldn't be able to change the host name because it has all capabilities in its own user namespace, has no capabilities up there in the initial user namespace. And so this is how this concept of superuser inside the container works without being superuser in the outside world. There is a program you can use, it's a little program of mine that we can use to do a bit of visualization of what's going on. See the shape of the namespaces, I can say sudo namespaces, sudo go run namespaces of.go. If I just run the command like that, it's going to show me all the processes on my system and all the namespaces. Too much information. Let's just compare the shell on the left here with another process that's in the initial instance of the namespaces. So let's try that PID, that's the shell over here, and PID1 on my system. Even that is too much information because that's going to show me 8 different types of namespaces. So I'm going to just restrict the view a little bit. I'm going to say, well, don't show me all the namespaces, just show me a few of the namespaces. And I'm going to say, show me the user namespace, let's say the mount namespace, the PID namespace, and the UTS namespace memberships of those processes. And, okay. There's my view. The hierarchy is represented through indentation. What you see there at the top is the initial user namespace, which has PID1 in it. Below that, there's the new user namespace that was created for my container. And you can see there that it owns, that's what the indentation is telling us also about, is telling us about ownership. It owns some mount namespace, a PID namespace, and a UTS namespace, and you can see the process there is a member of those namespaces. And then PID1, on the other hand, is a member of the initial mount namespace, the initial PID namespace, the initial UTS namespace. My program is very simplistic. There is a much nicer program floating around, written by someone who lives not very far from me by chance, called Alex KNS. And if you are curious, go and find out about that project. You can download it. It gives you nice graphical visualizations of the namespaces on your system. I'm supposed to finish this hour. Embarrassingly, I've almost finished the presentation. What do we want to do? Take a short break now, or I can go for another 15 minutes and I'll probably just finish.
Take the 15 minutes and go.
Take the 15, yeah. If you leave, I won't hold it against you. I will keep going then. So, then the question is, C groups inside the container. My container was set up with a C group for doing resource management. And we can see this because there was a C group that was created. In fact, what I can do is say cat/proc/ my PID of my shell on the left /C group. There's the C group that was created, and this is telling us this process is a member of that C group. Now, I can use C groups for doing resource limitation. What I'm going to do is step into another directory where I'm going to say copy a little program that I created earlier on. What this program does is just burn up CPU time and print out how much CPU time it's getting each second. And I'm going to copy that into my container. So I'm going to say copy into, oh, hang on a second. Which directory did I do all this in? Let's have a quick look. ls tool lsp consh. Looks like I did it there. Good. Okay. So I'm going to copy that binary, CPU burner. I did prepare this early, and I just want to mention in passing, it is statically linked. And the reason is I don't have any shared libraries in my container, so I need to have a statically linked binary. And so I'm going to copy that into tool lsp consh and into the directory demo, and then let's just copy it into the upper level file system, the upper level directory of the overlay mount. And hopefully I've done things right now. There it is, sitting there in the root directory of my container file system. And then I'm going to run that program. And what it's doing is every second printing out how much CPU time I got. That's remarkable. I think there's something, I wonder if my clock is a bit askew. My clock, there's something strange going on with the clock on my machine. It's running 8% fast. So this is a magnificent program. It gets 108% of time each CPU second. Yeah, okay, ignore that little glitch. Now, what I'm going to do from the outside world is now use that C group to limit the CPU time that this process can get. I was going to say it can get 50%, but it's going to get 54%, I think, at the rate things are going, but really it's 50%. So to do that, what I do is say sudo sh-c, and I want to say echo. Oh, look, I'm going to do this a different way. I'm going to step into the sysfs cgroup directory, and then give myself a root shell. Okay, change that shell prompt to something shorter, and then say echo two numbers. These two numbers are essentially expressing a fraction. And what I'm saying is 50%, half of a CPU. And I'm going to write that number into that, hang on. Okay. Write that number, sorry about that. Echo 50,000. 100,000 into cgr1/cpu.max. And there we go. Oh, it's sort of settled down now. Now my clock's doing the right thing. Okay, so I'm getting 50% of the CPU time. Okay, so this is, just an example of how C-groups can be used to do resource limitation. You can also do things like limiting memory usage, limiting network bandwidth. There's various resources that you can limit using C-groups. Okay. What else do I want to say? I've already done that demo. I'm not going to try. Look, I'm going to just go a little bit further and then call it a day. Yes, sorry, Ignat.
I have a question about Cgroup. So, like, the 50% is 50% of what? Of the parent?
50% of a CPU. Yeah.
What I mean is, like, if I have a Cgroup hierarchy,
Yes.
set 50% on, like, the third layer, is it 50% of the upper layer or the upper?
These numbers are always absolute. So a higher level percent is a cap for the lower level percent. Yeah. There's another way of using the CPU controller where you can say, I want to actually do subdivision. But that's not the mode I'm demonstrating at the moment. Yeah. So
What I'm trying to understand is, like, let's say I set up a hierarchy, I create a Cgroup which is 50% of the overall CPU, and then inside I create another Cgroup which is 50% of that Cgroup. So
yeah.
the absolute number will be 25?
No, when I use the CPU controller in this mode, these are always absolute numbers. If I said 50% at the top level and 40%, or let's say 50% at the next level down, it's 50% absolutely in both places. But there is another mode you can use where you can say, these two groups, I get half each, but then under this one, I'll create two child secrets. They get half each of what came from above, and they would get quarter then. Okay. Look, I'm going to skip the networking demo. I'll just say you can do it, but I just want to perhaps just finish off with one more thing. If this was a cool container, what would be a cool container, I think?
32 containers inside each other.
Or maybe just one inside another? Yeah? It'd be a cool container, I think, if I could have a container inside a container. Yeah? I can do it. Okay. One more thing that I should be able to do in a decent container. Container inside a container. Docker couldn't do that for years. I did it in days. Okay. So, there are a few challenges. One is Busybox does have an Unshare applet, but the Unshare applet doesn't know about all the namespaces yet. It doesn't know about Cgroup namespaces. I didn't talk about Cgroup namespaces, but the point is it just simply doesn't do them. It doesn't have the option for doing a Cgroup namespace. The way I'm going to fix that problem is I'm going to take the standard Unshare program, copy it into my bin directory. My consh setup script uses sudo, but Busybox doesn't have a sudo applet. That doesn't matter. My shell inside my container has superuser powers anyway. So what I'm going to do is edit my script just to remove the sudo strings. And then one more thing, the upper layer of an overlay file system cannot itself be an overlay file system. So the way I'm going to solve that problem is I'm going to mount a tempfs and use that as the upper layer for the overlay file system used in the lower level container. Okay, it's always best when we do it live, isn't it? It'll go wrong. Now, let's step back. I've got my scripts here, and I want to put those into my container file system. So what I'm going to do is say, copy those script files into demo lower. And now, if I look, there are the scripts now in my container file system. Then I want to edit the files so the sudo words are gone in those copies. So, whoops. I'm cheating here a little bit. I prepared this command earlier and had it in my history. And this is just the thing that edits out those sudo words. Oh, what did I do wrong? Oh, wrong place. Is it the wrong place? Yes, it's the wrong place, isn't it? No, hang on. Oh, did I put them in lower? That was it. Ah, yeah, of course I did. There, you can see it there. There we go. And I need an unshare. So I need to, I'll say RM out of demo lower bin, remove the unshare link, because I'm going to replace it with something else. And then again, I'm just grabbing this out of my history to save myself some time. This is my statically linked version of the standard unshare command, and I'm copying that into demo lower bin unshare. Have I now done all the steps that I need to do? I said I need the unshare, I need to do the edit, and I need to do the mount of the tempfs file system, of course. Now, I need to remind myself of what I need to do there. Yes, okay. So, those were the steps I needed to do outside the container. But what I want to do now is some steps inside the container, where I will say, I've got to remind myself of one or two things here. Here's my outer container here. I'm going to make a subdirectory called demo inner, and then do a mount dash t tempfs tempfs demo inner, and step into that directory, and then just do an ls dot dot. Yeah, so I've got all the pieces in place now, and I'm going to now run my create lower FS script, create the lower layer file system for the inner container in a directory, and again I'll just call the directory lower, and then create consh setup dash Cgroup group, let's call it Cgroup 2, different host name. Let's try Langvid. Oh no, let's try something else. Pukaki. And then the directory with my lower layer file system and where I want the file system to be set up, which is just the current directory. Oh no. It's a demo. What did I do wrong? Sorry? Yes, but why have I done this? How have I done this wrong? Interestingly, I've done something subtly wrong, but I have got a process with PID1, and I think that that's a different Busybox now. Let's just say, I did something subtly wrong there, but let's just say PID of Busybox here. There are two Busyboxes. That's my inner Busybox. I've just messed up something in the file system. And if I say grep ns tgid in /proc /114244, that's the second layer, status, 3 PIDs, because 3 levels of PID namespace. Okay, it's a nearly working container inside a container. I just did something subtly wrong. Okay, I think if I over here, if I type commands like ls, yeah, I messed up. But I did just do something subtle wrong. I missed some step. So I'm going to say I made a container in a container, but I just messed up a little bit on the way. You can check my slides to see where I went wrong. Okay? Best thing about live demos is they can go wrong. Okay, Ignat, of course, a question.
Unshare in the upper container manually and try to show us.
I could, but let's not compound my errors. Any other questions? Okay, you got 2 talks for the price of 1. You probably even sneak into another session now. Okay, I don't know why I went so fast. Getting too much practice, I guess. Thank you for your time, unless there's any more questions. Oh.